for systems that consist of more than two particles, like the helium atom, we need to come up with some ways to get answers for the quantum mechanics of those systems because we can't find them exactly. So this means we need to come up with some approximation techniques. What I want to propose is that we're going to define some kind of trial wave function, and this trial wave function will be parametrically dependent upon some parameters. So the way we write this sometimes is we might write this like this, where this is the parameter that this trial wave function depends upon. If you want to get an idea of what that might look like, an example could be, for example, if it were a Gaussian, we could have something like looks like this, that it's simply the weighting on the Gaussian factor. Okay, so this would be a parameter on which this function depends, and it affects how broad the Gaussian is. Okay, but this is just an example. I want to be more general than that and just talk about a trial wave function. So instead of writing all this stuff out, I'm simply going to write this like this. So when you see this, this means the trial function that we want to explore as a possible solution for the Hamiltonian. Okay, now since we don't know what the exact solutions are, we're just making an educated guess in this case. So for example, in the case of the helium atom, we might use the hydrogen atom wave functions as an educated guess, as a starting point or a trial function. But in order to use that and to understand how this approximation works, we're going to need to have some information about what are we likely to find with respect to the energy levels that we get from that trial wave function. So let's set some ground rules here. Okay, first of all, for the Hamiltonian that we have, let's assume that there are eigenstates that have the following energy levels. Now, I don't know what these eigenstates are. I don't know what the eigenfunctions are because I can't solve the problem. But what I'm interested in learning is what would be the relationship between the operation of the Hamiltonian on these states with the operation of the Hamiltonian on my trial wave function. So I want to get an idea of what these look like relative to one another. Okay, now this trial wave function is something that we can express in terms of those eigenstates, and I'll do that in just a moment. But at first, I want to talk about what would we get if we were to find the energy expectation value for this trial wave function. Okay, well, this is something that we have expressed before. We can express the expectation value of the energy, and I'm going to label this in a particular way so we can keep it distinct. I'm going to label it with the trial wave function, and it's going to be equal to this set of integrals where the trial wave function with the Hamiltonian trial wave function d tau divided by, because we don't necessarily have a trial wave function that is normalized, so we need to divide through by its square magnitude. Okay, another way we can write this, in a way that I will prefer to write this if I can, is like this. It's the same thing. Okay, this just means exactly the same thing. Okay, but this is a little bit simpler way for me to write it. I don't have to worry about the functionality of the wave functions and all of that. All right, so what I want to do is I want to get a handle on how to determine what this is, somehow related to the actual eigenstates of the Hamiltonian. All right, well, it turns out one of the tricks that I can use, and we'll talk about this in another video a little bit more extensively, but one of the tricks that I can use is I can express these trial wave functions as some kind of linear combination of my eigenfunctions. So I could say, okay, we'll have the 0th eigenstate, the 1st eigenstate, and so forth, and just keep adding them together. So in other words, I'll write this as some big sum over all of these various eigenstates weighted by these coefficients a sub k. So this is just a way of adding functions together to make another function. Okay, but there is a special reason for doing this, and again, it's something we'll talk about in more detail in another video, but this is giving us a way to get a handle on this problem. Now, I'll also point out that if I were to take this one, and remember that this notation suggests that this is somehow related to the complex conjugate of that, that this is going to be also true for these wave functions. So if I take the complex conjugate of all of these things, I will end up with something that looks like this. All right, now you may be really wondering, what am I talking about here? Why will I need that? Well, you'll see in just a moment, because we've got things like this in here and in here. So we'll need to account for that and account for this in just a moment. All right, so now what I want to do is I want to take this linear combination of our trial wave function expressed in terms of the unknown eigenfunctions of our Hamiltonian and use this to help evaluate this expression up here. All right, so in order to do that, I'm going to have to be able to calculate quantities like this, or at least express it in terms of those eigenstates. All right, so let's do that. If I plug this in for each of the trial wave functions, I can write this thing like this. Okay, so here's the sum to get this form of the operator. So I'll have a sub k star psi k. Okay, so that what I've written here is just this. Then I have the Hamiltonian. Then I have another sum, again over these states. Like this. Okay, well, this looks like a horrid mess, but it turns out it's not so bad, all right? And actually, I'm going to change this summation index just to keep it distinct from the first one, so we'll use m as our summation index. All right, so now when I operate the Hamiltonian in here, I can actually bring the Hamiltonian directly in there, because this is just numbers. This is just numbers multiplying that Hamiltonian. So I'll end up with sum over k, ak star psi k, and then I'll have sum over m, a sub m, and now the Hamiltonian operating on this. But let me remind you, the Hamiltonian operating on one of its eigenstates gives you an energy level of that eigenstate. So in fact, when I operate on this, and I'm going to have this in a different color, I'm going to have E sub m times this wave function. All right, so what I've done is operate that Hamiltonian on this. So this gives me a way of operating the Hamiltonian on this trial wave function, although admittedly there's still a lot I don't know, because I don't know what these coefficients are, and I don't even know what these eigenstates are. Okay, but let's go ahead and simplify this expression. If I write all this out, it's going to be sum of k, sum over m, a sub k star, a sub m, and then I'm going to have, oops, let's take an e sub m out of here, because this is just now a number, and I can take it outside of this closed set of brackets, and I end up now with this very tidy thing in the middle. But you remember, for a Hermitian operator, and a Hamiltonian is a Hermitian operator, the eigenstates must be orthogonal to one another. So in other words, this is going to be 0 unless k is equal to m. Okay, another way, another thing that we can do is ensure that our eigenstates are normalized. So in this case, we're going to say that this is going to give us, if you will, this particular part of it, I should say, this part of it will give us 0 if m doesn't equal n. That's for sure, but we're also going to say it equals 1 if m equals n for these eigenstates. So that's going to simplify this expression a lot, because it means that k must, shouldn't be m and n, should be m and k. K must be equal to m. That's the only term that survives. So this means that the net result of this will look like this. It's going to be a sum over the eigenstates. And now I'm going to have a sub m star times a sub m, which is giving me a sub m quantity squared times e sub m. Okay, so very tidy sort of expression now for this thing that I didn't know how to do. Now, I still don't know a lot in here. I don't necessarily know these energy levels, and I don't know these coefficients, but what we're really after here is to learn something about what this trial wave function means. Okay, similarly, I could go through and evaluate this thing using this summation. And I hope it's obvious that without the Hamiltonian in the middle there, I will end up with an expression that will look like this. Okay, in other words, without the E. So now if I want to write my expression for E, the expectation value of the energy, which is, remember, just this trial wave function energy, it's going to be the sum over m times these expansion coefficients squared, E sub m, divided by the sum over m of these expansion coefficients squared. All right, well, I'm still not quite where I want to be, because what I want to do is I want to compare my trial wave function energy with the lowest energy of the eigenstate. So in other words, I want to compare this with my lowest energy for the system, because what I really want to start off with at least is some measure of the lowest energy level. All right, so how would I do that? Well, what if I subtract E0 from both sides of this? So I could subtract, I'll subtract E0 up here, and I could subtract E0 down here, but to combine it somehow with this stuff, I'm going to write this over this. That's just equal to 1. But now I've got E0 in the numerator, so I can bring this inside the summation. And when I combine these things, I will end up with the following. I'll have sum over m, a sub m squared, and then each of the energy levels minus E0. And then this is divided by this sum over m, a sub m squared. All right, it may seem like I'm just making things more complicated now, but here's what I want you to notice about this. Okay, there's a couple of things. One, these quantities down here are all positive. They're all greater than 0. Okay, these are just numbers that we have squared. Now, some of those numbers could have been negative, but we've squared them, so they're all positive. Same is true of these numbers, as they're the same numbers. What about this quantity here? Well, if E0 is the lowest energy of the system, and EM is just the mth energy of the system, we must have that EM is greater than E0. Okay, so, well, what that means now is that this thing here is positive. It's greater than 0. This is greater than 0, this is greater than 0, and this is greater than 0. Everything here is greater than 0. So that means that E, or epsilon phi minus E0 is greater than, and I'll say or equal to E0, because if somehow we manage to get a trial wave function that was exactly equal to the lowest energy eigenstate, then it would be equal to I0. Okay, and what did I say? I said equal to greater than 0 is actually greater than 0, not E0. All right, so when I rearrange this, what I find is that my trial energy expectation value is always going to be equal to, greater than or equal to the ground state. Now, this is an important result, and why is this an important result? Well, it means that whatever my trial wave function is, if it's not the ground state, then it's going to result in an energy that is greater than. So in other words, it produces an upper bound on the lowest energy eigenstate. And this is something that's going to be very helpful for us. Now, I introduced this as something that was dependent upon a parametric parameter, alpha. All right, well, what we can do is we can minimize this E sub phi because it is implicitly a function of alpha if our trial wave function depends on alpha. It has to depend on alpha. So we minimize this by finding an optimal value for alpha. And when we minimize it, that then produces the very best guess that we can give for the lowest energy of this particular Hamiltonian. And that's the whole thing that we call the variational principle, which is the title given at the top of the slide. This is a demonstration of the variational principle.